Guys, today we are going to be talking about similar transformations, or EQ. How can you use properties of transformations to determine whether figures are similar? Our learning goal is to draw and describe similarity transformations in the coordinate plane, and to use properties of transformations to determine whether polygons are similar. Our key term today is similarity transformation. Okay? Alright, if you're not finished, I'll come back to it later. Alright, a transformation that produces similar figures is a similarity transformation, aptly named. A similarity transformation is a dilation or a composite of one or more dilations and one or more congruence transformations. You need to make sure you have written down what I am underlining in red. It's a dilation or a composite of one or more dilations and one or more congruent transformations. Okay? Two figures are similar if and only if there is a similarity transformation that maps one figure to the other figure. Yesterday, we talked about this. It was the big word yesterday. It was the P word. The sides of similar figures are proportional. Okay? We'll say it like this because it should be calming, right? Sides are proportional. Soothing, right? Proportional. They don't have to be congruent, they just have to be proportional. Proportional is the key, okay? Proportionality is the key. Use. Alright. If I applied the dilation D to the polygon with the given vertices, and then I was asked to describe the dilation, check out what happens. Okay? The dilation at xy gets applied with a scale factor of what? 3. So I multiply the original coordinates by 3. Every coordinate gets multiplied by 3. I start at 1, 1, 3, 1, and 3, 2. Check out A. A goes from 1, 1. How does it get to 3, 3? Multiplied by 3. 1, 1 to 3, 3. 3, 1 becomes 9, 3. 3, 2 becomes 9, 6. Okay? A, B, and C. A prime, B prime, C prime. Any worries with that? Any trouble? Any troubles? Nope. That one's pretty simple, right? You'll notice it says the dilation with the center at 0, 0. Okay, we'll talk about when the center is not at 0, 0 when we get there. For right now, just don't worry about it, okay? That's a whole nother lesson. Y'all got me? So don't even worry about that part just yet. We're going to assume it's always at 0, 0 for now. I'll change it when I change it, okay? Scale factor's 3. What happens, Mr. Hobbs? When the scale factor is less than 1. A figure does what? Reduces. Very good. So here I have a dilation of what kind of scale factor is this? Fraction, but more specifically, proper fraction. Sorry. I could have if I put 4 over 3, is that still a fraction?
Yes.
So what kind of fraction? Do you know why we call it an improper fraction?
Because it's just simplified.
Because the numerator is higher than the denominator. Y'all could learn in Algebra 1 how to make it, mixed numbers, right? You know what we call improper fractions in here? Mainly because I've been calling this since 2nd grade. They're called Dolly Parton fractions because there's more on the top and less on the bottom. Okay? Improper fractions. They are a thing, but we will typically be kind to you and just make them normal proper fractions, okay? 3/4 is my scale factor. I multiply each coordinate point by 3/4. Mr. Hobbs, I'm not good at multiplying fractions. That's okay. You have a tool that you can use to help you out, right? A tool that you can use to help you out. Use the tool to help you out. Use what you've got to get what you want, right? 3/4 times everything would reduce this particular triangle, negative 8, 4 becomes negative 6, 3, negative 4, 8 becomes negative 3, 6, and 4, 4 becomes 3, 3. Who's with me still? Okay, good. Still kind of almost there. Who's there? Who's at that point? Still kind of, okay, who is lost? Might as well put you in the TV show. All right? All right, so we're going to work on it again today. Pretty much just an extension of yesterday's lesson. So if you're good with it all, then that's good. If you need more work with it, let's see if we can't get it by the end of the day today. Y'all going to work this problem out. Apply the dilation, x, y, a fourth of x and a fourth of y to the polygon. Here's a hint. It's got 3 angles. What do you think we call it? Triangle. You'll be amazed. Okay, vertices are at D, negative 8, 0, E, negative 8, negative 4, and F, negative 4, negative 8. I want you to name the coordinates of the image and describe the dilation, meaning, did it reduce? Did it enlarge? Go ahead and get started with that now. And let me help you out here. All right, first thing to do is the following. Okay? Write down the original points. D is at negative 8, 0. E is at negative 8, negative 4. F is at negative 4, negative 8. We will then apply a transformation such that xy gets multiplied by a fourth of x and a fourth of y. We call that transformation a dilation. And that's what we're going to do to each number that we see. My new, when it says name the coordinates, I will name them D prime, E prime, and F prime. I've taken my calculator. I've multiplied 1/4 times everything. What is a fourth of negative 8? Negative 2. What is a fourth of 0? 0. So D prime is at negative 2, 0. A fourth of negative 4 is what? So this is at negative 2, negative 1. This would be at negative 2, negative 1, negative 2. Okay? Got me? If I asked you guys to graph, you would graph those, graph these parts, and graph these parts, right? Okay? Right, there's one last step involved. Describe the dilation. Reduction by how much?
4.
Perfect. Reduction by your scale factor, which is 1/4. That's it. That's all you gotta do, right? Pretty simple, very straightforward. Okay? Very straightforward. Yes! Okay. For now, at least. Oh! Partner, then I get this. Determine whether the polygon with the given vertices are similar. What would happen if this was similar polygons? The angles would be what? The angles would be, don't say even, say the C word. Congruent. And the side lengths would be, what's that? Everybody do it with me.
Proportional.
Come on.
Proportional.
It's very soothing, okay? Yesterday, how did we make it so that things were proportional? We had to do what? Find what's called a similarity ratio, right? A ratio. When I hear the word ratio, I need to be thinking in my head, fraction, 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 okay? Here's why. Your ratio is simply going to be the side lengths of the bigger figure over the side lengths of the smaller figure. The corresponding side lengths, we call that, okay? Let's just, you know what? Let's take the math verbiage out for just a second. Guys, it's really pretty simple. Take the length of the left side of the big one and put it over the length of the left side of the small one. Okay? So, math. Now we're doing math talk again. I'm going to take AB and put it over JH. Right? That's the left side of the figures. Then I'm going to take the top side, AC. I'm going to put it over JK. Alright? You got me? I'm going to put it as a fraction. Think very practically. How do I know how far, how far is it from A to B? What is that side length? How do you do that? Say it again. You just count. Okay? You just count. 1, 2, 3, 4, 5, 6, 7, 8, 9. How far is it from JH? How do you do that? You count, right? 9 over 3. How far is it from A to C? 9. How do you do that? If you don't believe me, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right? How about J to K? 3, right? Now, these are squares, okay? Well, one of the things you should know about a square, all the side lengths are the same. So if I asked you for the side length of CD, what would it be? CD would be 9, and KL would be what? 3. What about the bottom of it? D to B? 9 and 3. Good, for L to H. Y'all got me there? Everybody with me there? Okay? All right. Mr. Hobbs, what if it's not perfect like that? You use the distance formula. Okay? I'll use the distance formula. Now look, I did this to you last year and I'll do it again, right? If we use the distance formula, that's going to be lesson 2.0. Okay? Y'all got me? If I couldn't count it, if A was over right halfway between it and B was halfway between it, it's too hard to count, right? Okay? I can't actually count it. We use the distance formula. All right? We're not going to do that today. You don't have to worry about it just yet. Okay? We will start working on that, though, maybe tomorrow. Okay? So we're going lesson, yesterday was 1.0, today's about 1.5, tomorrow will be 2.0. Okay? We're just going to upgrade each day, little by little. All right. I want to reduce these fractions. 9 over 3. What does that reduce to? 3. And I'm going to do this for you. 3 over 1. 9 over 3, what does that reduce to? All right, guys. Once I get this in reduced form, I look at these and I ask myself, self, are those the same? Self answers back, yes, they are the same. That means they are proportional. Y'all understand? That means they are proportional. See? I already got you doing it. Proportional. If the sides are proportional, are the figures similar? Yes. Okay? Y'all see how this class works? It's really the question's simple. You're asking yourselves, are these similar, right? But to figure out that answer, you got to go through step after step after step, right? Okay? Right? Got to first figure out what to do, then you got to figure out how to solve it, and then you got to actually solve it. Okay? All right? So these would be similar polygons. Listen to my question carefully. If I started with JKLH and so that was my pre-image, right? That was my original figure. And then I got ACDB or ACDB, okay? What scale factor did I use? How do you know? It's what it is, right? The similarity ratio will tell me what my scale factor is, right? Practically speaking, how do you know?
If you multiply all the points by bigger, you get the bigger point.
You'll get the what?
The
the enlarged points, right? If I start with a figure and then the resulting figure is bigger, right? That means my scale factor had to be what?
More than one.
More than 1, okay? Alright, y'all got that?
Yes, sir.
What if I started with ACDB and I shrunk to JKLH? What would my scale factor be?
1/3.
Why is it 1/3?
2/3.
What do we call that? The reciprocal. Who said it? Yo, Mad Dog, good job, right? Check it out. If I go from, so if I got my scale factor, I've got this similarity ratio. My scale factor that I knew from beginning was 3, right? If I want the reverse of that, I just flip my fraction. Take this and flip it. Okay? That is we call that a reciprocal fraction. All right? So my scale factor is 1/3 if I am shrinking, and it's 3 if I am enlarging. So if I'm reducing, it's 1/3. If I am enlarging, it's 3. Okay? All right. Last problem I've got for you guys is this one. Let's see if we'll do this one together, okay? Mainly because I completely messed it up first block. But that's okay. Don't make it. All right, I'm trying to determine if these are similar polygons. All right, put your thinking caps on. What do you need to do? Figure out if there is what amongst the sides,
Portion.
Proportion.
right? Guys, the sides will be proportional in similar polygons, okay? So that's day 2. So when I say that in day 2, something should be going on in your head that starts to click, starts to say, okay, we say proportions, I need a little bit more help before I completely figure that out. Well, if these sides are proportional, that means that QP over XW, QP over XW will result in the same similarity ratio as QR over XY. Okay? I made these easy again. Let's count. Mr. Estebanco, how far is it from Q to P? Count it up for me. 4. How far is it from X to W? Trust them. 10. What is 4/10 simplified? 2/5. Right? Mr. Estebanco, how far is it from Q to R? Well, how far is it from X to Y? What is 2/3 simplified? 2/3. It's as simplified as it can be, right? Are those the same ratio?
No.
Is there proportion amongst the sides?
No.
No. Only when the ratios are the same in simplified fraction form, right? You see how it's got to match up? If it doesn't match up, it's not proportional, okay? You got me?
Yes, sir.
So they're not similar, right? Same shape, right? Yes, same shape. We can all tell. This is a rectangle, okay? All right? But there's not proportion amongst the sides. You with me? That's all I got today.